Hello everyone, welcome to this session. My name is Benjamin Smith. I'm a Senior Developer Advocate for AWS Serverless, and this session is called Best Practices for Growing a Serverless Application. Now, I think this is a really interesting topic because we're not going to focus so much on how to build a serverless scalable application, but rather how to grow your application, how you can organize your repositories and your development teams, and we'll talk about how to avoid some of the common challenges that we know customers run into as their applications grow. So this is what we're going to cover in this session. What I'm going to do is I'm going to start by showing you a fairly simple and typical implementation of a serverless application by looking at a Lambda function. And we'll look at how that tends to look on day one in production, and then we'll fast forward 100 days and we'll see some of the challenges that we start to see our customers fall into and show you how you can apply some best practices to overcome these different challenges. So a typical story that we do hear from our customers is that once they've experimented with Lambda, maybe they've tried out a few different workloads, they've played with the event-driven model, and they've started to build their application prototype. Because serverless technologies let you transition so easily and quickly from prototype to production, because of the inherent scalability and the managed infrastructure, before they know it, their application is running in production at scale. So they have a Lambda function that's receiving an event and performs some computation on that event and outputs the result to some destination. Fast forward to 100 days later, and this is the first challenge that we see our customers having to tackle. So as the usage of the application is starting to increase, maybe it's becoming more widely adopted and more successful, and it now has additional feature requirements. And the developers have kept up with this feature creep by building out their Lambda functions to handle additional functionality, accepting more inbound events and processing the events and producing outputs accordingly. But in an effort to keep up with this rapid demand of the business, our development team has kind of resorted back to some old habits. And what they've started doing is adding additional events to the same Lambda function, and they're having to build in additional logic to process these events. And so on and so forth. As the requirements grow, more logic is added to this same Lambda function. Now, the good news is that the application is still operating nicely in production. The Lambda function is scaling automatically, it's meeting demand, and the development team is still focused on coding new features without worrying about the infrastructure. So what's the problem? Well, the issue is that as more and more features are required and applied to this Lambda function, these development teams are finding it harder and harder to decouple one request from another. They have to ensure that each update or release doesn't cause any breaking changes to another. And this is slowing down their release cadence now, and it's adding more and more complexity to this Lambda function. The function now has to contain internal routing to handle each event. So what they've done essentially is built a monolith inside their Lambda function, and you might sometimes hear this referred to as a Lambda-lith. And this goes hand in hand with another common challenge that we see. So what started as a straightforward single repository, which was used to version control the function code, has now become really difficult to separate the ownership of responsibility between the different development teams. Because there's no clear boundaries of ownership, because this code is not very well decoupled. What this means then is that new developers have to take time to understand the complexity of this Lambda function, which is handling multiple events. And because all of this code is held within a single function, it's forcing each development team to use the same runtime language. And of course, one runtime might be less suitable to a particular task than another. The bottom line is that this monorepo approach is becoming difficult to maintain. So how do you solve these two growth challenges of a Lambda-lith and a monorepo? Well, first you can try and split your Lambda-lith apart into multiple Lambda functions. Each function should have a small, well-defined functionality and scope. So a golden rule here is to aim to reduce complexity wherever possible. So that means limiting the conditional logic in your Lambda functions. Often you'll see a one-to-one mapping of a single event invoke to a single Lambda function. And here's a good example of a common Lambda-lith that we often see customers sort of accidentally create. So it might seem reasonable to have an app whereby API gateway catches all requests and routes everything downstream to this one single Lambda function. Then this Lambda function contains the logic to branch internally to the appropriate code to handle each request. Based on the request, it could branch based on, for example, the method, the URL, the parameter, some data within the body. Depends on what the business logic needs. Now, this will work, and indeed I talk about this a lot in the serverless LAMP stack. It can be sometimes a reasonable model, but the problem with this is that although it sort of works and scales up operationally, what it does mean is that security permissions, resource allocation, memory allocation, and performance is applied to the entire function. So what would be a better way of building this application would be to split apart this Lambda function based on each CRUD operation. So here you can use the built-in routing capabilities of API Gateway to configure each request to route to a specific Lambda function. And that Lambda function is then designed to handle just that request. So this takes away the overhead of having to maintain routing logic within the Lambda function's code. That reduces complexity of the application and reduces the scope of each individual Lambda function. So that allows you to allocate the minimum required security permissions to each function, which we'll talk about in just a moment. So then if you recursively apply this process to your Lambda function, you will end up with a whole bunch of Lambda functions like this that are independent and reusable. And this is where you want to get to, because this reduces the impact of bugs or failures in one area of code that affect other application operations and allows each function to scale independently according to its individual demand. What you can then do is to create microservices from these functions. So each microservice becomes a building block that, when combined with other blocks, it makes up the application. Each microservice should deliver a well-defined set of capabilities on a specific domain. And you can communicate between these microservices using events or APIs, and this makes it nice and simple to update and replace components without impacting other blocks or other microservices. So with the concept of this shareable, reusable Lambda function, you might accidentally hit other situations that you want to avoid. So here's an example where a Lambda function is being used by more than one microservice. And this can cause breakages and suffer from all the same problems as a monorepo, shared responsibilities, ownership of which development team should own this particular Lambda function, for example. So this is a situation you want to try and avoid. And you can avoid that by following a couple of fairly simple rules. And the first is that you should aim to share the logic and not the function. So what I mean by this is that you might consider duplicating or cloning this function and using one version or one function for each microservice, or even merging the two microservices together so they're owned by one group. You should also use contract testing and versioning for your functions and assume that failures will occur. But your Lambda functions should typically be written for the good non-failure path and use other services to handle the fail path where possible, to handle things like retries and route off to services to handle that failure, instead of writing custom code inside your Lambda function to handle that failure. So as your microservices grow and your applications expand, you'll need a reliable way to communicate between them and within them. And here you have two great modes of communication with microservices. There's choreography and orchestration. Now, in orchestration, there's a controller, that's the orchestrator, and this controls the interaction between services. And it dictates the control flow of business logic. It's responsible for making sure that everything happens on queue and follows a kind of request-response paradigm. So AWS Step Functions is an ideal tool for this sort of interaction. Then in choreography, every service is more independent. There's no hard dependencies between them, and they are loosely coupled only through the events that they share. So each service listens for events that it's interested in, and then it does its own thing. And this follows the event-driven paradigm. So for this interaction, you can use something like Amazon Event Bridge. More often than not, you'll use orchestration to communicate within your microservices and choreography to communicate between them. So once you've created these building blocks or microservices, you have formed these natural boundaries to group or identify the development responsibilities. And you can now build repositories based on these ownership boundaries and assign these to your development teams. So for functions sometimes that are entirely independent and don't share any other AWS resources, it might be appropriate there to create that as a single repository. So that could be a helper function or simple event processing code. And what you can do is you can use a framework such as AWS SAM, Serverless Application Model, or other frameworks are available to help you organize those code repositories. So this first example here shows a monorepo approach. So in this approach, you have one repository which holds all the resources, all the functions, and all the events, and all the event sources that are all defined within a single SAM template, all in one repository. Then you have your microservice-based model, which allows you to create a repository for each individual microservice. And each repository will have its own SAM template that defines all the resources and event sources and functions that are relevant only to that microservice. And in some situations, it might be necessary to have a function-based repository. So here your SAM template would define all those resources and event sources relevant to the specific function. Okay, so another common challenge that you might face on day 100 is all related to security. So with this changing structure of a growing decoupled serverless application, you might hit some new security challenges. For example, do more resources mean that you have more permissions to manage? How do you maintain observability into the applications across multiple regions and multiple versions? And how do you make sure that only approved and secure code libraries are available to each function? That's what we'll talk about next. So first, to answer some of these questions, we need to adapt a little bit the way we think about security when compared to a traditional model. So a more traditional approach to security, or to securing an application, will look like this castle and moat approach here. So in this model, the perimeter, or a sort of secure perimeter, is established around all the resources that you're trying to protect. Whereas in a serverless-based model, you use a zero trust model here. So here the micro perimeters are built around each individual resource, and these perimeters enforce strict verification of every service and how they interact with each other. And the difference between these approaches can be seen quite easily here. If a bad actor breaches the castle moat model, they have access to the entire application that sits within that boundary. Whereas with the zero trust model, if a perimeter is breached, access is limited just within the bounds of that service. So that means your application as a whole remains more resilient to attacks or incorrectly assigned permissions. And this zero trust model is implemented using IAM resource policies and execution roles. So if we take the case of Lambda, or Lambda function, the resource policy will dictate which events or services are authorized to invoke your function, to trigger it to start running code. And the execution role grants the function permission to perform an action with another service or resource. So essentially it's the execution role which dictates what the function is and is not allowed to do. And in this example, you can see a resource policy which has been applied to a function, which allows API gateway to invoke that function. And then you can see the execution role, the purple box, which allows the function to perform only a put action on a specific DynamoDB table. And by using IAM roles to dictate the function's permissions, I'm able to decouple its security posture from its code and business logic. So that helps reduce complexity of my Lambda function and also makes it much easier to maintain. And you can go further still by creating permission boundaries to limit the scope of a function's execution role. And this can prevent users with write access from escalating the application's permission beyond the scope of its own resources. So what that means is even if the function's execution role has been granted additional permissions, they're only going to be effective if it's also been permitted by that permission boundary. So the best way to kind of visualize this is with the Venn diagram here. So my permission boundary is the purple circle, and this is able to perform a put and an update action on any resource in the EU West 1 region. And then my Lambda execution role is the orange circle, and it's allowed to perform any action on a given table in any region. Now, the effective permission that this Lambda function is granted is to perform a put or an update action on the MyDB table in the EU West 1 region. It's the overlap or the intersection of these two security permissions. And when this becomes really useful is if you start to scale this out across multiple Lambda functions. So each bounded by an application permission boundary defined by an admin user, and each with their own resource policy and execution role, then a function's permissions that reach beyond that boundary are still not authorized. So that lets you safely scale out permission boundaries to multiple Lambda functions that comprise your application. And there's a number of other services that you can use to help implement security best practices. You can use AWS X-Ray for monitoring and tracing. You can use AWS Secrets Manager and Parameter Store to hold sensitive application data. And you can use Lambda layers to share pre-approved code libraries. As serverless adoption grows, and it's becoming more and more important to monitor for insecure flows and attempts to force functions into some form of unsafe code path. So to maintain visibility as your application grows, you need to make sure that visibility is decoupled from the application business logic. And first of all, it helps to tag your functions, and that makes them nice and easy to track and group together. But you should also continuously monitor the entire zero trust ecosystem, and you should do that using a combination of historic and real-time views. So historic views help you to provide compliance reporting, whereas real-time views help to map out workflows and implement policies. And AWS X-Ray is a great tool for this. It's a service that helps you analyze and debug your distributed applications and provides an end-to-end view of requests as they travel through your application. And you can see maps of your application's underlying components. But there's also a growing number of tools and services provided by our partners to help you monitor and secure your serverless applications. Keeping secrets and sensitive data is another very important part of building and growing serverless applications. And the best way to do this is to use the managed services available to you. You don't want to be placing sensitive data in your code, as that might very well end up in some repository somewhere that you didn't wish it to be or that you might not know about. So it's best to store things like API keys and secrets in AWS Secrets Manager. And this also helps to keep a single source of truth and enables you to automate the rotation of these secrets. This example here shows how you can use a SAM template that uses an environment variable to hold the secret ID. And this secret ID kind of acts as a pointer to the secret in Secrets Manager, where the value is actually stored. That value is then retrieved using the environment variable in my Lambda function using the AWS SDK. Another common challenge is that of managing business compliant code libraries and dependencies. And this is where you can use Lambda layers for instances where these libraries have to be pre-approved by the organization prior to your use. This makes the maintenance of code dependencies more manageable because you're keeping a single source of truth. And these layers can then be controlled by a layer permission policy. So you can see an example of that here on the right, where we're using the AWS CLI to add a permission policy to a layer. This particular command line call is granting permission for all accounts in an organization to use version 3 of a layer within their Lambda functions. Okay, the next common growth challenge we see comes with managing multiple AWS accounts. So microservice architecture typically results in a number of independent and loosely coupled services communicating with each other, either synchronously, maybe via APIs calls, and asynchronously via events. And these microservices are often owned by different product teams. And these teams might even segregate their resources into different AWS accounts. And that could be for reasons that include security or billing or resource isolation. And this can sometimes result in the following challenges. You might have cross-account deployment challenges. So that's where a single pipeline needs to deploy a microservice into multiple accounts. For example, a microservice might need to deploy into multiple environments like dev and QA and prod, and maybe each one of these exists in a different AWS account. You also have a cross-account lookup challenge. So during deployment, a resource deployed into one AWS account may need to refer to a resource that is being deployed into another account. How do you do that? You have cross-account communication as well, where microservices executing in one AWS account may often need to communicate with a microservice that's executing in a different account. So what do these challenges look like, and how can we solve them? So first, we're going to approach this by using a fictitious airline booking app that consists of a number of different microservices. And the typical booking flow for this would be triggered by an end user making a flight booking using the web application front end. Now, this invokes the booking microservice via its REST API. And the booking microservice persists the flight booking and publishes that booking event to an SNS topic to enable sharing of that booking data with other interested consumers. So in this sample application, the loyalty microservice subscribes to the SNS topic and it consumes the booking event. And it uses the booking information to then calculate loyalty points for each customer. Now, let's say that these two services exist in different AWS accounts and they're owned by different development teams. How would you deploy this? So the first thing you do is use a separate third AWS account as the deploy account. And this will act as your central location for your CI/CD services. So that could be code commit, code pipeline, code build, whatever your particular flavor is, whatever you're using. And the booking pipeline will execute in the deploy account. That would deploy the booking Lambda functions and all the related resources into the booking account. The loyalty pipeline also executes in the deploy account and it deploys all the loyalty resources into the loyalty account. And this is what the CloudFormation template might look like. Here's a snippet on how the deploy account is allowed to deploy booking resources into the booking account. So you can see here there's two IAM service roles used to enable that cross-account activity. And both of these actually exist in the booking account. So the first is a service role that's assumed by CloudFormation when it carries out the change set replace action in the booking account. And the second here is the service role that's assumed by CodePipeline to execute this pipeline stage in the booking account. And it allows access to CodePipeline artifacts in the S3 bucket of the deploy account. Okay, so on to the next multi-account challenge, which is cross-account resource communication. Asynchronous communication is a pretty common pattern in microservice architectures. We've mentioned it a few times already in this little talk. This is where a publishing microservice publishes an event that consumers may be interested in without any concern for who those consumers may be. Now, in the case of this sample application, the publisher is the booking microservice here. And this publishes a flight booking event onto an SNS topic that exists in the booking account. The consumer is this loyalty microservice, and it looks up the yarn of the SNS topic at deployment time in order to set a subscription to it. Now, we know that it's bad practice to hard code resource arms into CloudFormation templates, right? So how can we achieve this cross-account stack referencing in a secure and repeatable way? One good solution to this would be to use what's called a CloudFormation custom resource. So we're going to use a special Lambda function as our custom resource. And what this means is whenever the custom resource is created or updated or deleted, CloudFormation will invoke this Lambda function using the Lambda API. And this function, what it does is it lists stack export variables from another account and it returns these values to the calling CloudFormation stack. What's really good about this method is that it doesn't create any hard dependencies between the two stacks. So this custom resource Lambda function is defined using SAM and it's deployed just like all the other Lambda functions. It's deployed in the booking, it's deployed like the booking and the loyalty microservice Lambda functions. The booking microservice is created by a separate SAM template and deployed into the bookings account. And the loyalty microservice is created by the loyalty SAM template and that's deployed into the loyalty account. Now, the loyalty template uses this custom resource Lambda function to look up the yarn of the booking SNS topic. The custom resource Lambda function uses an IAM role that is permitted to assume roles in another account, which in this case is a role that exists in the deploy account. And the custom resource Lambda function uses the SDK to obtain and return the stack exports from the booking account. And here you can see a Lambda function defined within the loyalty account template in that loyalty account, and that's defined with SAM, and it's invoked by an SNS event. And you can see how it uses custom resource Lambda function to subscribe to the SNS topic ARN, which exists in the booking account. And finally, the permission for the SNS topic to invoke that Lambda function is granted by the Lambda resource policy resource that exists in the loyalty account. So, to recap, there's a number of different challenges that you may come up against when you're growing your serverless applications, and broadly, they tend to fit into one of these four categories. So firstly, there's the challenge of the monolithic Lambda function, which can create a tightly coupled code base, and this can add unnecessary complexity to your application. And this can be solved by breaking apart that Lambda function into multiple functions to create independent, reusing building blocks of finite scope. And if you do have these large monolithic Lambda functions, you might also end up with a monorepo, which can make it difficult to separate responsibility of ownership and start to slow down your developer release cadence. And you can solve this by grouping functions and resources together around a specific domain to create microservices with natural boundaries of responsibility, which you can then use these boundaries to create repositories and separate development team ownerships. Then there's the challenge of enforcing security best practices. So with distributed serverless application, there's more resources and more permissions to manage. But using this zero trust model with the application of things like an application permission boundary and IAM roles, with regular monitoring, you can continue to grow your applications securely. Then finally, managing multiple AWS accounts is a different challenge. And this brings up things like cross-account deployment and resource lookups. And these can be met by using custom resources to enable that cross-account stack referencing. But really, the fundamental principle to growing your serverless applications is to reduce code and to reduce complexity wherever you can. And often the best way to do this is to use the right service and the right tools available to you for each task. So for more resources on everything I've spoken about and everything serverless, you can visit serverlessland.com. There's a plethora of resources on everything serverless there. If you want more specific resources on growing serverless applications, then you can use this short link here, s12d.com, svs315. And this is a curated landing page to accompany this talk. We'll have code samples for you, blog posts and everything that you can dive into more detail to see how you might want to lay out your repositories, how you can organize your development teams, and how you can secure your applications as they grow. Thank you so much for taking the time to join me and listen to this session today. If there's any questions that you have that we didn't manage to get to in the chat, or any questions that you think of later, then by all means reach out to me on Twitter. My Twitter name is Benjamin_L_S, and I'm always happy to talk about anything serverless or anything AWS related. Thank you so much for your time, and I hope you enjoy the rest of the sessions.